Okay, let's jump right in. Imagine you're studying chemistry, maybe for your exams, and you keep hearing terms like organic compounds. It can feel a bit, well, confusing at first, right?
Oh, definitely. It sounds complex, but it's such a core part of chemistry. And once you get the basics down, it really starts to click.
Absolutely. So, welcome everyone to this deep dive. We've looked at some Class 10 chemistry material, really aiming to make organic chemistry clear and hopefully easy to grasp if you're just starting out.
Exactly. Our mission today is basically to unpack what organic chemistry is, why it matters, and cover some fundamental ideas without getting lost in, heavy jargon.
Let's build that foundation. So, first thing, what are organic compounds? I mean, originally the word organic meant stuff from living things, didn't it?
That's right, historically. Think sugar from plants, starch, urea from animals, even things that came from ancient life, like coal and petroleum. That was the old idea.
But it's changed now for chemists.
Yeah, the modern definition is a bit broader. Now, organic chemistry is mainly the study of compounds that contain carbon. There are a few exceptions, like uh, metal carbonates, oxides of carbon, but carbon is almost always the star.
And you find these carbon compounds pretty much everywhere in daily life, don't you?
Absolutely everywhere. The
Yep.
food you eat, your clothes, cotton, wool, synthetic soaps, medicines, plastic.
Fuels too, right? Petrol, diesel, LPG.
Exactly. Fuels are a huge one, so they're really, really fundamental.
Okay, so if it's all about carbon, what makes carbon so special? Why does it get its own, like, whole branch of chemistry?
Great question. Carbon has this really unique ability. Each carbon atom can form four bonds with other atoms. Think of it like having four hands it can use to hold on to other
My
atoms.
hands? Okay.
Chemists call this tetravalency. Tetra meaning four. And that's not all. Carbon atoms are also really good at linking up with each other.
How so?
They can join together, like holding hands that form really long chains, or chains with branches coming off, or even close up into rings. It's like building with Legos almost.
Wow, okay. So it can bond with four other things, and it can bond with itself in all sorts of ways.
Precisely. This property of linking with itself is called catenation. Chains, branches, rings. It creates amazing variety.
And I remember something about different types of bonds between carbon atoms.
Yes, good point. Carbon atoms can connect using single bonds, which is like one handshake, or they can form double bonds, two handshakes, or even triple bonds, like three handshakes between the same two atoms.
Okay, so four bonds possible overall, catenation to make structures, and single, double, or triple bonds between carbons. I can see why it's special now.
It leads to a massive number of possible compounds.
Now let's talk about hydrocarbons. That sounds simpler, maybe?
It is, in a way. Hydrocarbons are the a simplest type of organic compound. They contain only carbon and hydrogen atoms, hence the name. Hydro for hydrogen, carbon for carbon.
Just those two, carbon and hydrogen. Got it.
Yeah, they're like the basic skeleton. And we split these into two main groups, saturated and unsaturated.
Saturated and unsaturated. What's the difference?
Okay, so saturated hydrocarbons have only single bonds between all the carbon atoms in the chain or ring. They're called alkanes. You can think of them as being full up or saturated with as much hydrogen as they can possibly hold.
Saturated. Single bonds. Is there an easy way to remember that connection?
Definitely. Just think. Single bond means saturated. Say it with me. Single bond means saturated.
Okay, single bond, saturated. Got it. Alkanes.
Right. And their general formula is C sub 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 2 plus 2 sub. A very common example is methane, CH sub 4 sub, which is natural gas. Just one carbon, four hydrogens, all single bonds.
Okay, alkanes are saturated, single bonds. What about unsaturated then?
Unsaturated hydrocarbons are ones that have at least one double or triple bond between carbon atoms somewhere in the molecule. Because of that double or triple bond, they have fewer hydrogen atoms than an alkane with the same number of carbons. They're not full up.
Ah, so unsaturated means they could potentially hold more hydrogen if that double or triple bond was broken.
Exactly. That's a great way to think about it. Now, there are two main types of unsaturated hydrocarbons you should know.
Okay.
Alkanes, which have at least one carbon-carbon double bond.
Tehisi.
Their general formula is C sub sub subzone sub. C sub 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 is a key example that's used to make polythene plastic.
Ethene. Double bond. How can we remember that one?
Easy. Think. Alkene has a double bond. Hear the E sound. Alkene double.
Alkene double. Nice one. Okay, what's the other type?
The other type is alkynes. These have at least one carbon-carbon triple bond. Let's say their general formula is C sub 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 2 and 2 sub. Ethene E sub sub 2 sub 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 2 sub, also known as acetylene used in welding, is the simplest example.
A triple bond. Alkanes. Any trick for that?
For alkenes, you can think. Alkene sounds a bit like line, And a triple bond is like 3 lines together. Or maybe stretch it. Alkene has a triple bond. Let's say that. Alkene has a triple bond.
Alkene. Triple, okay, I think I've got those. Alkene's single saturated, alkene's double, alkene's triple. The last two are unsaturated.
You got it. That's the foundation of hydrocarbons.
Now, briefly, the outline also mentioned functional groups. What are they about? Sounds a bit more complicated.
Well, they add the extra flavor, you could say. Hydrocarbons are the basic structure, right? A functional group is a specific atom or a small group of atoms that attaches to the hydrocarbon skeleton.
Like adding something different onto the carbon chain.
Exactly. And this is something different. The functional group usually determines how the whole molecule behaves chemically. It gives the compound its specific properties and often dictates its name.
So they're really important for how the compound acts.
Hugely important. For instance, attaching an OH group, that's oxygen and hydrogen, turns a hydrocarbon into an alcohol. An alcohol behaves very differently from the hydrocarbon it came from.
Okay. Any other quick examples?
Sure. If you see a CHO group, that's an aldehyde. A CHO group makes it a carboxylic acid, like in vinegar. Even single atoms like halogens, chlorine, Cl, bromine, Cl, can be functional groups when attached to a carbon chain. They're called halides then.
So alcohols, aldehydes, acids, halides. These are all defined by these special groups attached to the carbon structure.
That's the idea. You don't need to memorize them all right now, but just understand that these groups add specific character to the basic hydrocarbon framework.
Right. Okay, so let's just quickly recap then. Organic chemistry, it's essentially the chemistry of carbon compounds.
Yep, mostly carbon.
And carbon's special because it forms 4 bonds, tetravalency, and links to itself in chains and rings catenation.
Key properties, absolutely.
We looked at the simplest ones, hydrocarbons, made of just carbon and hydrogen. They can be saturated alkanes with only single bonds.
Remember, single saturated.
Right. Or unsaturated alkanes with double bonds.
Alkane double.
And alkanes with triple bonds.
Alkane triple.
Got it. And finally, we touched on functional groups, which are like attachments that give organic compounds their specific properties, like alcohols or acids, COOH.
That's a perfect summary of our starting point.
Great. Hopefully that makes the whole idea of organic chemistry feel a bit less, scary if you're just starting. It's all about building blocks.
Absolutely, piece by piece.
So here's something for you to think about building on this. We know cooking oil, which is mostly made of unsaturated fats, is usually liquid. But candle wax, mostly saturated hydrocarbons, is solid. Why do you think that difference exists? How might those single bonds versus double bonds affect whether something is liquid or solid at room temperature? Something to ponder.
A great question to leave things on. It shows how these structures relate to everyday properties.
Exactly. Well, thanks for joining us on this deep dive into the basics of organic chemistry.